There we go. All right, cool. It seems to be working now. Perfect. All right, so I guess I'll just start by saying that based on some feedback from the reviewers when I submitted this, following up on that gap's kind of gone to the back burner, so I will mention it a bit, but there's going to be a lot more verification and a lot less on the actual implementation than before. So where this kind of comes from in the first place. So I'm sure most people here are familiar with equivalence checking, but just a motivating example that kind of will lead into what we're seeing later on. You might have like a controlled Z rotation, and you might have a decomposition like this, which is pretty common. That's some syntax with the semantic interpretations, for example, matrices. If you just compute this by expanding these out, you get some matrices that look very different, but if you do some algebraic manipulations, you can go from one to the other. And the problem of equivalence checking is, given the syntactic representation, the circuits representing the same operator. Whoops. So there's a lot of approaches to this and verification in general. I've just tried to group them together to kind of highlight where we are. So you have a lot of like rewriting based techniques that usually look at fragments of like, let's say the ZX calculus, for example, or like specific fragments of circuits. These fragments have decidable efficient procedures to figure out if circuits are equal. There's also some work with automata. Kind of in the middle, you have exact methods. The simplest example would be matrices or more sparse representations, for example, BDDs, binary decision diagrams, path sums, stuff like that. And then on the further side, you have more deductive methods. These can be automated, but they usually require, at the very least, automation. I'd put stuff over there like quantum Hall logic or the kind of work that people like Robert Wren do in Coq. So there's kind of like a trade-off between how much these techniques scale automatically and in terms of automation and the scope of what you can actually verify with them. Automation usually takes away some applicability. And in this talk, we're going to be focusing on this middle circle. Just for concreteness, I'll be looking at the case of matrices, but the techniques I'll be talking about are specific to matrices. You should be able to apply them to other techniques like BDDs, but I haven't actually explored that yet. And the kinds of problems that motivated this and why we started looking at matrices in the first place. So in some prior work, we ended up collecting a huge, I guess you could say like a compendium of circuit decompositions, most of them involving two, I think the biggest one had 8 qubits. There was 65 of them taken from a bunch of different papers, different notations. So there was just some question as to whether or not all of those decompositions, once we finally unified them and instantiated them, were actually correct. And there's also a lot of other examples of these small circuits that usually get overlooked in the verification work. For example, the rewriting rules in the equational theories I mentioned early on. And like I said, on this side, you have small number of qubits. And with these equational theories, you wouldn't want to use like these rewriting tools to verify them because that's kind of cyclic. You're using your rewriting systems to verify your rewriting system. So of course it's going to be correct because the rewriting system says it's correct. Of course you could try to like use a bunch of different ones, but still it would be good to just rely on something a bit more concrete for like the underlying verification methods when you verify them. So that's kind of like my justification for why I'm going back to matrices. But like I said, these techniques can be applied to other domains, like BDDs. And in this verification work, I guess 3 main challenges came up. The first one is if we're looking at things like matrices and we have rotations, you're going to get a lot of interesting matrix entries. And working with those exactly is one problem. In general, you see these decompositions coming up where you're going to like arbitrary sine and cosines. And if you actually want to verify rotation decompositions, you actually have universal instantiation. You want to prove it for all parameters. And I don't think I'll have too much time to talk about this, but there's some interesting things that come up with how you should actually specify ancilla qubits. Because every time you have like these like discards at the end, it's really some kind of an implicit assertion about the state of the qubit, but I don't think I'll have too much time to talk about that at the end. So yeah, the rest of this talk will really focus on these first 2 ones and maybe a bit about ancillas if I have time. So I'll talk about the exact matrix computation first. This is the underlying techniques here aren't too new, but the actual analysis we work through I've never really seen in the literature before. So, and this is kind of where I will talk about gap, but not too much. So when you want to do like matrix components exactly, there's usually two ways that's done. On one side, you have what's called algebraic extensions. You may have seen this diagram before. That's one of the papers that really explores this a lot. It was number theoretic characterizations of some gate sets, but the idea here is you can start with the rational numbers, and you can treat like other numbers like the square root of 2 or like pi as either like from a, I guess, an algebraic perspective, like adding extensions to the fields. And those can either be algebraic or transcendental, which I won't talk about transcendental extensions, and I'll explain algebraic a lot more in the next few slides. And on the other side, you have a more axiomatic approach where basically you just treat the real numbers as some axiomatic structure, completeness and all of that are axioms. Since I'm aiming for automation, I'm going to focus more on these algebraic extensions. Why that's automated will become clear in a few slides. So what exactly are algebraic extensions? You could spend an entire course just talking about that, but the idea is you start with some polynomial, you find the root of that polynomial, and you add it to your field. A standard example is if you want to add the square root of 2, that's a root of the polynomial x squared plus 2 equals 0. And once you add that in, if it's algebraic, you can prove that it actually gives you a finite dimensional vector space, or something that's not too bad to work with. The degree of the polynomial is the degree of your vector space. And it's not just a vector space, it's actually an algebra, so it's closed under all of the operations you need to do for matrix manipulations. And one important example are the roots of unity. Those are basically just the algebraic numbers on the unit circle, and they're also the solutions to x to the n minus 1. So those are just like the numbers that are like, well, basically like for example, the first root of unity would be I, because I to the power of 4 is 1. And when you look at like these roots of unity, we call these cyclotomic extensions for reasons I won't go into, but they have some nice properties. One is that they're closed under complex conjugation. Formally, it's an automorphism of that extension, but I'll come back to why that matters later on. I'm just kind of visualizing one example of what conjugation is doing there. These ones are fixed, and you're just kind of like switching these around, so you can do that and stay in your extension. And they're also dense on the unit circle, which we'll see why that matters later on. The simplest way to see that is if you think about like let's say the second roots of unity, like plus or minus 1, then I, and then going on and on, this dividing by 2. You're just kind of like cutting the unit circle into halves and quarters, and eventually you can approximate any point. But there's, I guess, fancier ways you could do it too, but the point is you can definitely do it. And even more importantly is you can do these computations efficiently. I still don't totally understand this work. I'm kind of looking into it more. But basically, there's this idea of a Zimbalist basis, which is like an efficient way to reason about arbitrary cyclotomic extensions. So it might be kind of hard to read with the lighting, I guess, but this is actually like a printout from GAP. If I want to add a 10th and 7th root of unity, you get this completely unreadable expression, but it's actually found in the smallest way you can decompose those two things. So like I can just pick arbitrary roots of unity and add them together, and all of that's being handled efficiently in the background. So that's why GAP is a nice choice for this kind of stuff. But I guess the takeaway here is you can add these roots of unity in prior work. For example, the Clifford plus T can be viewed as a cyclotomic extension. There's a lot of QDIT work that also shows that kind of stuff. So these kinds of extensions actually describe gate sets we care about. And if you want more, you can extend other things like the square root of 2, which we won't really talk about here because you don't have all of these nice properties. But if you need more, you can do it. You just won't be able to do what I'm going to talk about in this next section, which is how we actually verify rotations. So I guess a good way to start is just kind of where the state of the art is. So two techniques that I've looked at verifying parametrized circuits. One is in the Munich quantum toolkit that's been talked about a bit today. This technique, they start by using ZX reweighting rules, but the system's incomplete. And if the reweighting fails, then they fall back on a probabilistic sampling method. You just have to pick one point, and with probability 0, you'll get the wrong answer. And with another tool called Quartz, they do some symbolic rewriting. They basically look at the matrices with the sines and cosines, try to simplify them. Then they look at each matrix component, expand it out. So under the hood, it really is a matrix-based method. They encode all the equations that have to be satisfied, and then use SMT solving to try to find out if they're actually equal. That, of course, is going to involve nonlinear integer arithmetic. And so I guess given these explanations now, the limitations that we tried to address here with the MQT toolkit, the sampling theorem actually assumes you're just kind of sampling, but like you're actually doing uniform sampling over an interval, which is like hard to actually implement. So in practice, like that theorem is like an idealized case, but the sampling won't actually, you're rounding off somewhere, so it's more like an approximation of the actual theorem. And it would be nice to know what that error actually is. And with Quartz, since they're just kind of throwing it at an SMT solver, which works great, it would still be nice to know what the theoretical bounds are to actually say a bit more precisely. In this case, it would be double exponential on a number of parameters, and I don't have the complexity results written here because it's still ongoing work, but you can prove it's actually a bit better than that. So my work turns out to be an instantiation of the Miller-Bakewell framework. I didn't know about this, and it seems to have gone fairly overlooked in the literature. I actually found out about this 2 weeks before this conference right now when I was talking to Alex Kissinger. His student did this work, but the idea is you can take your gates and do a change of variable to get Laurent polynomials. Those are just like regular polynomials, but you can have negative powers. And then you can look at the degrees of those polynomials and try to give like compositional rules to over-approximate those. And then if you know the degree of each of the variables, those variables are like your parameters, and that gives you an upper bound of the number of points you have to sample. And if you do like one more than those number of points, and you just check those instantiations, you actually get universal, you prove the universal case. So this is kind of similar to those many techniques that we used in more classical verification, where you compute a cutoff, check those finite cases, and then extend it to the parameterized setting. But the work that in our instantiation, we're looking at the sine and cosine terms, whereas in Miller-Bakewell's work, you're actually looking at like exponential, so you have to do a slightly different transformation, but it actually lets you compute better bounds on what the degrees actually are, it turns out. And we do add one assumption that these sines and cosines can just be rational linear sums of your angles, which is similar to prior work. Basically, a lot of these techniques it becomes way too complex if you can just put arbitrary things in there, and most of the real examples do look like this. In none of the prior work have they really identified examples where it didn't work, so I still want to look into a bit more about the applicability, but work so far does seem to suggest that that's a reasonable thing to do. And like I said, my goal was to find closed form expressions for these bounds. And since I kind of did this without knowing about Miller-Bakewell's work, it's interesting to compare the techniques, and it leads to an interesting result. The prior work was based on like polynomial interpolation. That figure is actually taken from the original paper. And the technique I was developing is based on combinatorial Nahr-Selinstats. I'm not going to define that, but the simplest case is easy to explain. If you have a polynomial of, let's say, degree phi, then if I pick 4 points, at least one of them won't be a root. So that kind of tells you how many points you need to use to do polynomial checking, or like polynomial equivalence checking. And there's actually, from algebraic program checking, a probabilistic variant of this that you can apply as well, where if you pick a fixed number of points, you can calculate the probability that if you just sample one from that fixed set, that they would be equal or not. So this can actually give you more precise probabilistic bounds on that discrete sampling from the infinite space. And in my last few seconds, this looks like a lot, but it's all stuff that I'm sure everyone here has seen, just spelled out a bit differently. if you pick a point on the unit circle, you can write it like sine or cosine, and using complex conjugation, so you can actually get your sine and cosine from the roots of unity. So basically picking a root of unity is the same as picking your sine and cosine values, and as I explained earlier, that's dense, so you can, up to some precision, get any angle you want, and if you fix some n, you can compute the nth roots of unity, and you get you can sample from those endpoints, so that also gives a way to do the sampling. And as I said, compared to the state of the art, there really isn't that finite analysis. I'll just skip over the ancilla stuff, but the idea is you have your initialization of ancillas is kind of like assumptions, and then your termination is like assertions. There's some patterns that make this more reasonable to do. For example, the scoped ancilla pattern, and you can kind of define these properties inductively, and they're not too hard to check, but I don't really have too much time to talk about that, so that brings me to the end of this presentation. So just to recap, this work looked at reasoning about this exactly, proving equivalence with rotations, and also some preliminary work on specifying, I guess you could say, qualitatively good ancilla usage.
All right, thank you. Questions? I'm not sure that this doesn't seem to turn on. So.
Okay. Yeah, I'm one of the quartz authors. The reason why in solving these integer thingies works is because we only do small scale. Are you ready to do experiments? How is that standing?
So I was ready to do experiments, then I ended up reading the feedback and developing this new stuff here. So I'm just still doing a bit, like the proof also gives me the bounds. I have a good idea what the bounds are, but I haven't quite completed the proof yet. So once that's done, I think I can use the implementation I was doing before and then start doing experiments. So I hope to be doing that probably within the next months.
Other questions? Quick question from me. I know there's a bunch of different algebraic structures that famously Giles and Selinger, but a bunch of others in various verification papers have used to verify something like Clifford plus T or a subset of quantum computing. If you restrict yourself to these smaller algebraic groups, does that simplify things, and is that a strategy you've used?
So that definitely does simplify things. Where it doesn't work so well is if you, well, I guess once you have these parameterized, like these like cutoff theorems, maybe you could, depending on what you're trying to verify, but the problem in the beginning was we have these arbitrary rotations. Eventually you would probably approximate them with Clifford plus T, but if you want to prove it before doing any decompositions, you'd have to reason abstractly about the parameters. But once you have cutoff bounds, maybe you could prove that it's sufficient to look at the ones that can be realized in Clifford plus T if the cutoff bounds are low enough, for example. So that's an interesting point I hadn't thought about.
Yeah, I think that would be cool. Thank you. Thanks. All right, let's thank the speaker again.